Talk about complex zeros of polynomials. Let's start with this polynomial. P of x equals x to the fourth minus 3x squared minus 10. And suppose we were asked to factor. We could factor this in our traditional way because it's a trinomial and the exponents are a 4 and a 2. So let's just factor it this way. By trial and error, we would put x squared here and x squared here. Our 10 could break up into 5 and 2 with a negative on the 5 and the positive on the 2. And it's factored over the integers. And we would consider it finished because this doesn't factor further and this doesn't factor further. But that's if we were talking about integers. Let's explore this a little bit more. Let's find the zeros for this polynomial. And now let's not just restrict ourselves to integers. We know we could find the zeros by setting each of these factors equal to 0. So with this one would give us x squared minus 5 equals 0. So we would have x squared equals 5. So x equals plus or minus the square root of 5 are the zeros for this that come from this factor. And x squared plus 2 equals 0 would give us x squared equals negative 2. Or x equals plus or minus I square root of 2. Now, depending on what the directions were, we could write this in another way. P of x equals, let's suppose the directions were to factor over the reals. Now, these numbers are real. They're irrational, but definitely still real. So we could factor this x squared minus 5 into x plus the square root of 5 times x minus the square root of 5. And notice if you multiply that out, you will get x squared minus 5. Now these two zeros aren't real. So if the directions were to factor over the reals, we wouldn't be able to continue. We would just leave it as x squared plus 2. But suppose now the directions were to factor over the complex. Then the factorization would look like this. X plus the square root of 5 times x minus the square root of 5. And now these zeros would come into play. X plus I squared of 2 times x minus I squared of 2. And you could multiply those together and confirm that you would get x squared plus 2. And now we have it factored over the complex. Often, prior to pre-calculus, the directions that say factor imply that we're going to factor over the integers. About now, when we get to pre-calculus, often factoring over the complex is implied. But I do want to point out this. This was a 4th degree polynomial, and it factored into 4 linear factors. That brings us to this. There's an important theorem algebraically called the fundamental theorem of algebra. Even its name implies that it's important. That says every polynomial with complex coefficients has at least one complex zero, assuming that the degree is at least greater than or equal to 1. The nice thing about that theorem is it gets us to this very important theorem related to what we're talking about today, and that is the complete factorization theorem that says if P of x is a polynomial that has degree greater than or equal to 1, there exist complex numbers such that P of x equals this product, some coefficient that's a constant times n linear factors, where n matches the degree of the polynomial. So look at this again. X minus a 0, X minus a 0. Keep multiplying, X minus a 0. And you may have some constant potentially out here. Well, you'll always have a constant. Sometimes it will be 1. Sometimes it would be another number. So let's see that theorem in action. Let's factor this polynomial completely. You'll notice that this is the difference of 2 cubes. And we know how to factor that. We don't need any fancy strategies for that. So we would have x minus 2 times x squared plus 2x plus 4. Just using our formula for the difference of 2 cubes. But now, when we're saying factor completely, I mean with respect to the complex. So this is not considered finished. This factor is finished. You can't factor that any further. But this one can't be factored further with respect to the integers, but it can with respect to the complex. Let's find the zeros. We said x squared plus 2x plus 4 equal to 0. And solve. You could complete the square or use the quadratic formula. Since the leading coefficient is 1 and the linear coefficient right here is even, I'm going to complete the square. So we'll subtract 4, take half of 2, and you get 1. 1 squared is equal to 1. So let's add 1 to both sides. So we have x plus 1 squared equals negative 3. Take the square root of both sides. And subtract 1. So we have negative 1 plus or minus I square root of 3. So these are the zeros that came from this factor. So our factorization would look like this. X minus 2 times, and it is always x minus those zeros. So it is x minus negative 1 plus I square root of 3. And, oops, another set of parentheses. And x minus negative 1 minus I square root of 3. Now, rather than having those double set of parentheses, I could just distribute those negatives. So I have x minus 2 times x plus 1 minus I squared root of 3 and x plus 1 plus I square root of 3. And we have this binomial factored completely. Let's do another one. Let's do this problem. And the directions this time are to find all complex zeros. It doesn't ask us to factor it, just state the zeros. So let's do that. Now this one doesn't work with our traditional strategies of factoring trinomials or factoring by grouping, but we can use our rational zeros theorem. You know the possible rational zeros are on this list factors of 2 over factors of 1. So a very small list, plus or minus 1 or plus or minus 2. So we can start with 1 and see if it works. Notice if you substitute 1 in, you get 1 cubed plus 1 minus 2, and that does equal 0. So that means when we use our synthetic division, we are guaranteed that we'll get a 0 right here. Notice I included that 0 for the coefficient of x squared. Don't forget that. So we bring down our 1, multiply and add, multiply and add, multiply and add, and there we have our remainder of 0. So what we have so far is that p of x equals x minus 1 times, here are our coefficients of our other factor, x squared plus x plus 2. And again, on this problem, we have a trinomial that doesn't factor over the integers. So I'm going to set that factor equal to 0. And this time, rather than complete the square, I'm going to use the quadratic formula. Because while this leading coefficient is 1, the coefficient of x here is odd and not even. Of course, we could complete the square, but I'm going to use quadratic formula. So we have opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. And if we simplify this, we get -1 plus or minus the square root of -7 over 2. And let's write that in a little better form. We have x equals -1 plus or minus I square root of 7 over 2. So now the zeros for this one, this problem specifically said to state the zeros. The zeros are 1, we found it here, and it's related to this factor, and these two numbers, which are -1 plus I squared of 7 over 2, and its conjugate, -1 minus I squared of 7 over 2. And I wanted to point out that this quadratic formula generated these two numbers that were conjugates of each other. And that brings me to this theorem. And before we get to the theorem, do notice that we had 3 zeros for this third degree polynomial. The theorem that I wanted to mention is called the conjugate zeros theorem, that says if you have a polynomial that excuse me, that has real coefficients and the complex number z is a 0, then its complex conjugate is also a 0. So this theorem guaranteed that this would happen. If this number is a 0, then its conjugate was a 0 as well. So let's use this idea in the next problem. Find a polynomial with integer coefficients that satisfies these conditions. It's a third degree polynomial, and its zeros are -5 and 1 plus I. Well, we were only provided 2 zeros, and we know we have a third degree, but our conjugate zeros theorem guarantees that if we're given 1 plus I as a 0, we know, even though it wasn't stated, that 1 minus I will also have to be a 0. So our polynomial could look like this. X minus -5 times x minus 1 plus I times x minus 1 minus I. Now it did ask for a polynomial with integer coefficients. We haven't presented the polynomial with integer coefficients. So let's do some multiplying. I'm going to distribute that negative first. So I have x plus 5 times x minus 1 minus I times x minus 1 plus I. Now we have a choice about how to multiply these two together. You could multiply it together as you would if it were two trinomials being multiplied. Distribute the x across, distribute the -1 across, distribute the -I across, and simplify. But I want to show you another possibility. This is just a little aside here. So the goal being to multiply x minus 1 minus I by x minus 1 plus I. So let me remind you about this. We'll come back to the problem. If we're multiplying conjugates together, like x plus 7 times x minus 7, we would have x squared minus 7i plus 7i minus 49, and those middle terms drop off and we get x squared minus 49. So often we don't even bother writing those middle terms. So if we have x plus 8 times x minus 8, we know that the product is just x squared, that first term squared, minus 8 squared. Now we can use that idea in multiplying these together. If I consider x minus 1 as a group, let me write it with parentheses. So I have x minus 1 minus I times x minus 1 plus I. Now notice putting in those parentheses didn't change the value of that expression, but now it looks like conjugates in the same way these were conjugates. So the product would be x minus 1 squared minus I squared. And now we can easily simplify this. We have x squared minus 2x plus 1 minus I squared, which is plus 1. So we have x squared minus 2x plus 2. So here is the product of that expression. Right here. Here's the product of this expression. So let's substitute that in right here. So our result was this. X squared minus 2x plus 2. And again, if you didn't particularly like this little trick, if that felt like a trick to you, then you could just multiply it out again as you would if it were two trinomials being multiplied together. And now we can multiply this binomial by this trinomial, distribute the x across, distribute the 5 across, and we get x cubed minus, let's see, plus 3x squared. We have negative 10x and 2x, and plus 10. So we have our polynomial that has these zeros that is of degree 3. I want to do one last problem with you. And it's this one. It's to factor this is a 2 here, this polynomial. Now this is a fairly straightforward one if you notice that it factors over the integers. And you could use your traditional strategies for factoring your trinomial. Again, I use trial and error. You can use whatever strategy you like. So I have 3x and x. I'm going to put a 2 here and a 1 here with a plus and a minus, and it's done. But the issue is this. Suppose that you didn't notice that it factored over the integers. And that could happen. You didn't notice. So you set 3x squared plus 5x minus 2 equal to 0. And you just decided to use the quadratic formula. Let's do that. Opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. If we simplify, We get negative 5 plus or minus the square root of 25. That's going to be plus 24, so that's 49 over 6. So we get negative 5 plus or minus 7 over 6. And if you simplify each of those, negative 5 plus 7 over 6 will give us 1/3. And negative 5 minus 7 over 6 gives us negative 2. So the point I want to make is that often when people see these as their zeros, they do this. They know that they have zeros of 1/3 and negative 2. And they remember the part of the complete factorization theorem that says when you're factoring a polynomial, we can write it as x minus the 0 and x minus this 0. And they present this answer. Oops, not that. Minus negative 2 would make this a plus 2. But remember, the complete factorization theorem says this. Your polynomial will be factored into x minus the 0, x minus the 0, x minus the 0, with some leading coefficient that you need to consider. If you actually multiplied these two together, you would not get this polynomial. And notice it isn't equivalent to this. We know this is the answer. The leading coefficient here is 3. If you multiply this out, the leading coefficient would be 1. So we need to handle that by putting a 3 here. Now if I multiplied this x by x, I'd get x squared. Multiplied by the 3, that would give us the 3x squared. So you could present your factorization this way. It is completely factored. Or it could be presented this way. And notice if you distribute the 3 into this binomial, you would in fact get that factor. So those are completely equivalent. I just wanted you to see that because people often forget about considering this constant up front.